In this video, we will answer the question, what is sound? And we will define some of the basic concepts of sound. First, the textbook definition of sound is produced when an object vibrates and causes the air around it to move. So what does this look like? Let's start with a sound source. When that source vibrates, it creates a wave that emanates from that center point in all directions. And because of the vibration, some of the points have compressed air molecules and some of the points have expanded air molecules. The compressed areas or high pressure areas are compression, and the low pressure or expanded areas are rarefaction. And for this demonstration, let's look at that in a linear fashion as the sound moves away from the source. The darker areas represent the high pressure or compressed air molecules, whereas the lighter areas represent the lower pressure or rarefacted air molecules. The apparent direction of travel of sound is away from the sound source, but in reality, the air molecules or particle motion moves back and forth where the molecules themselves don't actually travel away from the sound source. And this is a lateral or longitudinal waveform. In order for us to illustrate this, though, we use a transverse waveform where the line above the center point or the equilibrium point represents the areas of higher pressure or compression, and the places where the line is below the equilibrium point represent the low pressure or rarefaction areas. And again, sound does not travel through the air as a transverse wave. It moves laterally or longitudinally through the air as air molecules are compressed and rarefacted over time. To look at this visually, in the upper right corner, the black line represents the sound source vibrating, and as the source vibrates to the right, it compresses the air molecules, and as it vibrates to the left, it stretches them apart. And then the visual representation is the line that's moving up and down. If you think about it as a spring or a slinky, if two people are holding the ends of the slinky, you do not shake it up and down to represent the sound as it travels through the air. You press the slinky closer and further away from the other end to compress and expand the coils. That's how sound actually travels through the air. Now here is a quick video about sound.
This is what a sound wave sounds like. But what does a sound wave look like? Well, the air through which the sound wave is traveling looks something like this. But if you want another visual representation of the sound, we can hook this speaker up to an oscilloscope and it gives us this graph. We say that this shape represents the sound wave because if we focus on a single molecule of air, we see that it moves back and forth just like a sine or cosine graph. The horizontal axis here represents time, and the vertical axis can be thought of as representing the displacement of that air molecule as it oscillates back and forth. The center line here represents the equilibrium position or undisturbed position of that air molecule. If we turn up the volume, we see that the oscillations become larger and the sound becomes louder. The maximum displacement of the air molecule from its undisturbed position is called the amplitude. Be careful, the amplitude is not the length of the entire displacement. It's only the maximum displacement measured from the equilibrium position. Another key idea is the period of a sound wave. The period is defined to be the time it takes for an air molecule to fully move back and forth one time. We call this back and forth motion a cycle. We measure the period in seconds, so the period is the number of seconds it takes for one cycle. We use the letter capital T to represent the period. If we decrease the period, the time it takes for the air molecules to oscillate back and forth decreases, and the note or the pitch of the sound changes. The less time it takes the air molecules to oscillate back and forth, the higher note that we perceive. An idea intimately related to the period is called the frequency. Frequency is defined to be 1 over the period. So since the period is the number of seconds per oscillation, the frequency is the number of oscillations per second. Frequency has units of 1/seconds, and we call 1/second a hertz. Typical sounds have frequencies in the hundreds or even thousands of hertz. For instance, this note, which is an A note, is causing air to oscillate back and forth 440 times per second, so the frequency of this A note is 440 hertz. Higher notes have higher frequencies, and lower notes have lower frequencies. Humans can hear frequencies as low as about 20 hertz and as high as about 20,000 hertz. But if a speaker were to oscillate air back and forth more than about 20,000 times per second, it would create sound waves, but we wouldn't be able to hear them. For instance, this speaker is still playing a note, but we can't hear it right now. Dogs could hear this note though. Dogs can hear frequencies up to at least 40,000 hertz. Another key idea in sound waves is the wavelength of the sound wave. The idea of a wavelength is that when this sound is traveling through a region of air, the air molecules will be compressed close together in some regions and spread far apart from each other in other regions. If you find the distance between two compressed regions, that would be the wavelength of that sound wave. Since the wavelength is a distance, we measure it in meters. Be careful, people get wavelength and period mixed up all the time. The period of a sound wave is the time it takes for an air molecule to oscillate back and forth one time. The wavelength of a sound wave is the distance between two compressed regions of air. People get these mixed up because there's an alternate way to create a graph of this sound wave. Consider this: before the wave moves through the air, each air molecule has some undisturbed position from the speaker that we can measure in meters. This number represents the equilibrium undisturbed position of that air molecule. Then, as the sound wave passes by, the air molecules get displaced slightly from that position. So an alternate graph that we could make would be the displacement of the air molecule versus the undisturbed position or equilibrium position of that air molecule. This graph would let us know, for a particular moment in time, how displaced is that air molecule at that particular position in space. This graph shows us that in some regions the air is displaced a lot from its equilibrium position, and in other regions the air is not displaced much at all from its equilibrium position. For this kind of graph, the distance between peaks represents the wavelength of the sound wave, not the period, because it would be measuring the distance between compressed regions in space. So be careful, for a sound wave, a displacement versus time graph represents what that particular air molecule is doing as a function of time. And on this type of graph, the interval between peaks represents the period of the wave. But a displacement versus position graph represents a snapshot of the displacement of all the air molecules along that wave at a particular instant of time. And on this type of graph, the interval between peaks represents the wavelength.
For the remainder of this course, we are going to be dealing with audio in the human hearing range. So the audio spectrum, as we just heard in the video, is from about 20 hertz to about 20,000 or 20 kilohertz. The human hearing is most sensitive in the area between about 150 hertz and 5,000 hertz. Now, those frequencies lower than 20 hertz are infrasound, and ultrasound frequencies are higher than 20 kilohertz before you get into radio waves. Frequencies outside the audio spectrum are generally not consciously or audibly detected by our ears. However, infrasound, when loud enough, is detected as a vibration, and ultrasound between 20 and about 30 or 40 kilohertz is often felt as pressure inside your head, as though you had congestion. Now, the sine wave is the basic building block of pretty much all sounds, and a sine wave can be visualized by observing a weight suspended on a string or a pendulum. And sine waves have a very pure sound because they consist of a single frequency, and they are often called pure tones. The sine wave is a mathematical representation of a point on a circle stretched out over time. The characteristics of a sound wave, and this is a recap of the video we just saw, consist of the speed of sound, which is 1130 feet per second at standard pressure and temperature. And don't worry about what those are right now. And it's represented by the letter C and has the units of feet per second. Amplitude is the loudness of the sound, and that is measured in decibels. The period is the length of time for one cycle to pass, and that's 1 over the frequency measured in seconds. The wavelength is the distance for one wave or one cycle to complete itself, and that is measured in feet. And finally, the frequency is the number of cycles per second, or it is also 1 over the period, or 1 over the length of time for one cycle to pass. So here are 3 questions. What is the frequency if 500 waves occur in 1 second? What is the wavelength of a 500 hertz wave? And if you see lightning, then you hear the thunder 5 seconds later, how far away was the lightning? Pause the video, use these equations, and see if you can come up with the answers to these questions, and then we'll solve those when we come back. Okay, for the first question, what is the frequency if 500 cycles occur in 1 second? Well, the equation for frequency is cycles per second, or cycles divided by seconds. So therefore, we've been given 500 cycles in 1 second. So the answer is simply 500 hertz, or 500 cycles per second. So if we take that 500 hertz wave, what is its wavelength? So the equation for wavelength is the speed of sound divided by the frequency. So speed of sound was given at 1130 feet per second, and the frequency is 500 hertz. Therefore, 2.26 feet is the length of the wavelength of a 500 hertz wave. The third question, if you see lightning and then you hear the thunder 5 seconds later, how far away was the lightning? Well, this equation is the distance is the speed of sound times the number of seconds. So we know the speed of sound is given at 1130 feet per second, and it took 5 seconds for the thunder to get to your ears. So multiplying that out comes out to 5,650 feet, which is roughly 1 mile. So if you see the lightning, then hear the thunder 5 seconds later, the lightning was approximately 1 mile away from you. The next concept we're going to look at is complex sounds. And as we've heard, a sine wave is the only sound without harmonics. It's also called a pure tone. Most sounds are made up of a complex combination of vibrational patterns that create a complex waveform. A sound that has a definite pitch has a repetitive waveform, no matter how complex that waveform is, and therefore it will repeat at regular intervals. If a complex waveform is a highly random pattern, we perceive that sound as noise. And all complex waveforms can be broken down into a series of components called harmonics, or normal modes, using a process called Fourier analysis. Conversely, you can combine the harmonics through a process called Fourier synthesis. Now, harmonic overtones are frequencies higher than the fundamental frequency, and the harmonic frequencies lower than the fundamental overtones are called differential harmonics. Overtone harmonics are related to the fundamental frequency through multiplication factors, 2 times, 3 times, 4 times, etc. So if we have the first harmonic, which is also called the fundamental, and we assume it's at 55 hertz, the second harmonic is going to be, for those of you that have a musical background, 1 octave above the fundamental and twice the frequency, so it's 110 hertz. The third harmonic is 1/5 above that octave, and it's at 165 hertz. The fourth harmonic is 2 octaves above the fundamental, and it's 4 times the frequency at 220 hertz. The fifth harmonic is a major third above that second octave at 275 hertz. The sixth harmonic is a fifth above that second octave at 330 hertz. And the seventh harmonic is a minor seventh above that second octave at 385 hertz. And then the eighth harmonic is 3 octaves above, and it is at 440 hertz, which is also the concert tuning frequency of A440. Now, harmonic overtones can be used to create complex waveforms such as the square wave, the triangle wave, and the sawtooth. So looking at the sine wave, it is just the fundamental frequency with no overtones. The square wave is all of the odd overtones or harmonics, and the number in green represents the amplitude. So the fundamental frequency is at an amplitude of 1, and then the third harmonic is at an amplitude of 1/3, the fifth harmonic at an amplitude of 1/5, etc., continuing up through the audible range. The triangle wave is the amplitude is 1 over the harmonic squared, so 1/9 at 3 times the fundamental frequency, plus 1/25 at 5 times the fundamental, etc. And then the sawtooth wave is all of the overtones, the second, third, fourth, as opposed to just the odd ones like the previous 2 waves. And the amplitude is at 1 over the harmonic number. If you want to pause the video here and go to the website at the very bottom of your screen, there is an online additive waveform generator where you can hear the difference between sine, triangle, square wave, and sawtooth waves, and you can also adjust the different overtones to see how they affect the sound. Here is a video that discusses harmonic overtones in relation to some musical instruments that use a membrane or a soundboard or a column to project their sound. Those that use a membrane are stringed instruments, and those that use a column would be your woodwinds, your brass instruments, and your drums would be another example of a membrane instrument. And these are called membranophones, and here is an example.
An important component of sound design is gaining an understanding of how harmonics and overtones work. So for an example, let's take a look at 2 common orchestral instruments, the clarinet from the woodwind family and the trumpet from the brass family, and take a look at how they differ in harmonic content. First, here's a clarinet playing an A440. Now, if I freeze that there, we can take a look at the fundamental frequency very clearly coming through at 440 hertz. We also can see the 880 hertz, the 1320, and so on. So the fundamental 440 hertz times 1, times 2, times 3, times 4, times 5. Very predictable pattern here, all working to reinforce this fundamental A440 pitch. It's only when these overtones end up being slightly off or very off from that mathematical relationship do we start losing a sense of a pitch center, and we have what are more characterized as overtones and not harmonics. In the case of harmonics, this would be called the fundamental or harmonic 1, harmonic 2, harmonic 3, harmonic 4, etc. We could also call these overtones. They are harmonic overtones, and in this case we have the fundamental, the first overtone, the second overtone, the third overtone, etc. Another characteristic to pay attention to here with the clarinet, even though all of the harmonics that we would predict are present, we do notice that rather than a smooth attenuation that we might expect, we notice that the second harmonic or the first overtone drops down a little bit, and then the third harmonic, which should be a bit lower, actually pops up again. And we have kind of a back and forth a little bit here, where the odd harmonics, somewhat like a square wave, tend to have a little bit more emphasis, at least early on, than do the even harmonics. And that's a characteristic of a cylindrical shaped instrument like a clarinet. By contrast, a conical shaped instrument like a trumpet is going to have a lot more intensity in all of the harmonics and a more even distribution of each of the harmonics in the series. So let's take a look at that. Okay, so a very similar pattern in terms of having the 440 hertz, 880, 1320, and so on. But there's much greater intensity with the overtones, particularly in this area where you see that the harmonics are much more intense compared to what we saw with the clarinet. So this is typical of, as I say, a conical shaped instrument like a trombone, meaning that where the mouthpiece is the smallest diameter of the horn, and as you get out towards the bell, it flares out further and further, creating more of a density of overtones, giving that bright quality that we expect from brass instruments.
The next concept we will talk about is differential harmonics. And differential harmonics are generated by summing two or more waveforms with the same amplitude and near identical frequencies. For example, a 1000 hertz sine wave and a 1200 hertz sine wave will generate a virtual 200 hertz differential harmonic that is not present in the original sound source. There is no energy produced at the 200 hertz frequency, although the brain still synthesizes this internally. So here is what a 1000 or a 1 kilohertz tone sounds like. And this is what a 1200 or 1.2 kilohertz sine wave sounds like. And when we add the two of those together, our brain will synthesize the difference between the two of those because they're fairly close together. So even though 200 hertz is not present, we will hear this 200 hertz tone mixed along with the 1000 and the 1200 hertz tones. Now, to make that a little bit more obvious, in case the 200 wasn't obvious because of your computer speakers or earphones that you're using, here is a 1000 and a 1005 hertz tone mixed together, and you'll be able to hear the differential 5 hertz beat frequency as a wavering in the volume of the sound. And to make that even a little bit more obvious, here is 1000 and 1002 hertz. And you can hear the 2 hertz difference as the wavering in the sounds. So differential harmonics are also present in human voice and most other musical instruments. And the adult male has a fundamental frequency of around 200 hertz and the adult female somewhere around 250 hertz. But this fundamental frequency that we perceive is not actually directly produced by the vocal cords. It is a differential harmonic created by the frequencies generated by the tonal range of our vocal cords and the resonances of the head and chest cavities. And this is how we can tell one person from another when they speak, is based on this differential harmonics. Now, another concept related to differential harmonics is something called a wolf tone. And a wolf tone is an effect or a side effect created by instruments in the stringed instrument family, such as violins and cellos, that make it very difficult to tune and play on these instruments, play in tune on these instruments. And it has to do with these differential harmonics created by the instrument itself. And here is an example of what a wolf tone sounds like in a stringed instrument.
Many cellos have something that's called a wolf tone. Some violins have it as well. This cello I have here has a particularly bad one. To find the wolf tone, you're going to start on the G and slide up the string until you find a hideous wobbling pitch. It will be quite obvious when you hit it. You could hear that when I got to the G sharp, it was very unstable and the sound was wobbling.
Now, inharmonic overtones are produced by instruments that use their body as the sound generating surface, such as bells, cymbals, marimbas, xylophones, metallophones, and they do not produce harmonic overtones. They produce overtones that depart from the whole number multiples of the fundamental frequency. These instruments are called ideophones, and they produce inharmonic overtones, and they're based on the material from which these instruments are constructed. And therefore, because the harmonics are inharmonic, or the overtones are inharmonic, these instruments almost always sound like they're slightly out of tune. And if you do need to tune them, you need to change their body size or add or remove mass from the instruments. The effect of the differential harmonics and inharmonic overtones create a process called intermodulation. And here's a video demonstrating inharmonic overtones.
All right, now let's take a look at an instrument that does not have a strong pitch center. What we should see is a series of overtones that do not make integer ratios with the fundamental frequency like we saw with the clarinet and the trumpet. In other words, if a pitched instrument is being analyzed, we'll see the fundamental an octave above that, which would be 2 times the frequency of the fundamental, then 3 times, 4 times, 5 times, etc. This isn't a go-go. It's an instrument that we describe in Chapter 2. Let's take a look at it. All right, so what we see in our spectrum analysis here is we have a fundamental frequency of around 1077 hertz. So what we should predict for the first overtone would be in the vicinity of 2154, somewhere in that territory. And when we come up here, we're a little bit off from that. We're in that ballpark, but not quite precisely, and it needs to be really precise in order to reinforce that pitch. The same thing we notice as we continue along here with the dominant overtones not having an integer relationship with the fundamental. The result is there is a quality of pitch to the sound, but it's not a type of pitch you could hum along to. It's not a pitch that you could easily identify. So there could be a higher and lower, but it's hard to describe this as being a certain pitch on the musical scale. By contrast, let me clear this and let's take a look at instead a flute playing an A440. So like the clarinet and trumpet we saw before, here's the dominant 440 hertz fundamental, the first overtone at 880 hertz, the second overtone or the third harmonic up here at 1320 hertz. So very clearly reinforcing the fundamental pitch. With a percussion instrument with its overtones, not so much the case.
Now, the next concept we're going to talk about is non-repetitive sounds, which are also known as noise. Non-repetitive waveforms do not have a recognizable pitch, and they sound noise-like. Their frequency spectrum consists of a collection of components at unrelated frequencies all across the human hearing range. In the audio field, we will deal with white noise, which is equal power across all frequencies. And if you wanted to think of it, it sounds very similar to a waterfall. Pink noise is filtered at 3 decibels or 3 dB reduction for every octave you move up in the musical scale. And it sounds more like a light to moderate rainfall. Brown noise is filtered at 6 decibels per octave, and it decreases, the high frequencies decrease at a rate of twice that of pink noise, and it could be related to the hard, gentle surf that comes with a storm, or the hard or gentle surf that comes with a storm. And finally, black noise is silence. So here is a spectrum analysis of what the different types of noise look like, with the lowest frequencies at the left of each of the graphs. If you notice, the white noise is pretty much level all the way across, and it has the sound of a waterfall. Whereas the pink noise has the 3 decibel drop, or 3 dB drop per octave as you increase in frequency, and it's going to have more of the sound of maybe rainfall. And then brown noise, which is going to have the darkest sound because it drops off at 6 decibels per octave, and this sort of sounds like the surf during a storm. And of these 3 noises, the white noise and the pink noise are most commonly used in audio technology, and they're used to tune an audio system or to tune a room. Now, sound synthesis, complex waveforms for electronic instruments like synthesizers are generated using harmonic filtering or by summing artificial waveforms that are rich in harmonic content. One type of sound synthesis is subtractive synthesis, and this is removing harmonics by filtering out or filtering complex waveforms. Additive synthesis is the summing of 2 or more complex waveforms. Fourier synthesis is the summing of sine waves in a harmonic order. Frequency modulation synthesis is the summing of sine waves in repeated equal frequency distances, creating differential harmonics. And formant synthesis is manipulating the formant or the shape of a sound in a complex waveform. And this concludes this video.